Good evening, guys. We're going to talk about monitoring faults tonight, so make sure you're filling out your notes as we go. So you see a picture of the San Andreas Fault there. You've seen that picture before. It's a transform boundary, which means it's a strike-slip fault. And you can see on the right side, it doesn't take millions of years to see a difference between the plate movement. So on the right side, that fence used to line up, but it doesn't anymore because along that strike-slip fault, it has been moving from side to side. Okay, so it's important to monitor faults so we can see how much stress is building up. So there are four main ways that we can do that at this point. The first one is a creep meter, the second is a laser ranging device, the third is a tilt meter, and the fourth is a satellite monitor. So we're going to look at each one of those. So first things first, creep meter. Basically, the way this is set up is that you have a wire that you stretch across the fault line. So when that wire is stretched across the fault line, then it's tight and it's attached to a weight on one side, which you can see on the left side there. And as the fault moves and you have one plate moving farther than the other, they get farther apart. It's going to pull on that string. And that string will raise up or lower depending on if there is any movement. And you can see that they have a measurement tool attached to that string and the weight on the other side. So they know that if it's at one measurement at one day and they come back a week later and that measurement has changed, that there's been movement and they've either gotten farther apart or closer together depending on how that fault is moving. A laser ranging device, so this is used as well as the other one for strike-slip faults, and this time instead of a wire stretching across the strike-slip fault, they point a laser at it. And it has the receiver on the other side, and so over time, if the fault moves and one plate moves too far to the side, then that laser is not going to line up with that receiver anymore. So they can measure it that way to see if the laser is on center of that receiver or if it's kind of off of center or off the receiver completely, that they know that there's been movement there. The third one is a tilt meter, so this is what you're going to use on either a normal or reverse fault because you have that up or down vertical movement. So on this one, you see that the right side of the fault has moved vertically. So they would start out with those two water tanks with a tube connecting it, and the water would be even on both sides. So if the fault moves at all, if it rises, then you're going to end up with a lot of the water sloshing to one side. So you're going to have more water on one side than you would in the other instead of it being equal. So that at that point you can measure how much the tilt has been based on how much water has sloshed to one side. The fourth one is satellite monitors. Again, they're going to use this on normal and reverse faults because basically they send down sound waves, basically like, or not sound waves, but they use it like sound waves. It's by radar signals sending lights down, and they're measuring how long it takes for them to bounce back, much like a ship mapping out the ocean floor using sound waves. So this is going to help them measure the vertical movement of normal and reverse faults because as they send it down, if it comes back in 30 seconds the first time and then it takes 40 seconds the second time, then they know that the distance is greater, therefore the movement has dropped and there's been vertical movement down. Okay, if they send it down and it's 30 seconds the first time and then the next time they send it down it's 25 seconds, that means the distance has shortened and that part of the fault has risen up and gotten closer to the satellite. So that's how they use that to measure normal and reverse faults. Okay, so what is our risk here in Georgia? The answer to that, not too bad. Okay, so far we cannot predict when earthquakes will occur. We can measure how much stress that we have building up, but you never know when the rocks are actually going to snap. So the higher risks are going to be near your active plate boundaries. That's where you have a lot of movement going on with those plates. Okay, overall it's pretty rare to have earthquakes east of the Rocky Mountains because at that point you're sort of towards the middle of the North American plate, so we're not going to have a whole lot of boundary fault lines there. So Atlanta is under a moderate risk for earthquakes because there actually is a fault line that runs through Rome, Georgia, and kind of in that area. And so in Atlanta, we actually will have some earthquakes, but that fault line is so small and not very active that the earthquakes that we end up getting generally are so small that you can't even feel them. So you can look at this earthquake risk map for the United States, and it shows you where you don't really have any risk, where the moderate risk is, the major risk, and then the minor risk. So you can see Atlanta there is located in that moderate section, and that fault line kind of goes up through northwest Georgia. And the last thing we're going to talk about today are tsunamis. So these are waves that form from earthquakes that happen underwater. So if you look at the diagram on the left-hand corner, you can see that's a reverse fault. And the left side, the hanging wall of that reverse fault has moved up with an earthquake. It's shoved that side up vertically, and all that water sitting on top of it. So if that ocean floor gets pushed up, it pushes the water up too, and it creates this big ocean wave. Now notice the wave doesn't get taller until it gets to the shoreline, and it's basically like a big old flooding that happens, and the wave comes in and very quickly will flood the area, and then it will recede and go back. And it's possible that you'll have 3 or 4 different waves. It's not just going to be one. Think about when you throw a stone into a pond. You don't just get one wave coming out from it, you get several. So that can happen with tsunamis as well. They can be as tall as a 6-story building or as small as 1 meter tall, which is about 3 feet. So usually they're not big enough to cause a problem, and if they're 1 meter tall, you wouldn't even know that one hit you, hardly. You could be swimming in the ocean and wouldn't know the difference. Okay, but obviously the bigger the tsunami, the more damage it can cause. And the key to surviving a tsunami is to make sure that you have yourself prepared for those areas and you have an early warning system, which they're working on. So we have tsunami damage that you can see. This picture obviously is from the flooding of a tsunami that didn't recede completely, but you can see the damage to the trees as the water came in. It's usually a huge amount of water that just comes in and tears down anything in its path. And then obviously this is a much worse picture where the water has come in, and you can see the boat traveled in with the water, and then the water receded and everything is completely destroyed. Okay, bring your notes to class as usual, and I will see you tomorrow.